Have I mentioned that we have to go back to Enceladus? We have to go back to Enceladus. It is this place in the solar system where liquid water is being sprayed out into space, water that we know has been in the presence of geological activity, water that is infused with dissolved hydrogen gas, the food for bacteria, water that contains organic molecules. Like if there's one place in the solar system where we could find evidence of life that is beyond Earth, Enceladus is the place because it makes this material so readily available. You just have to fly through it and analyze it. So what will it take for us to be able to understand whether or not there's life on Enceladus? Now, there is a fairly large flagship mission that has the potential to be developed called the Orbilander, and this was one of the priorities in the decadal survey. But there have been other ideas to investigate the plumes at Enceladus and try to help answer this question: is there life there? So my guest today is Dr. Marshall Seaton. He is a astrochemist, works at NASA, and is one of the investigators behind a concept mission called the Astrobiology Exploration at Enceladus, or AX. And this would be a New Frontiers mission, so fairly low budget, and would be able to quickly get out to Enceladus, investigate, try and give us some evidence whether or not there's some kind of biological process at Enceladus, which again, I think is one of the most interesting questions we could possibly ask. So we have a wide-ranging conversation about the science case for Enceladus, what the AX mission would comprise and how long it would take to get that science back. And then we also just talk in general about the search for life in the solar system, the kinds of icy moons and places that might be interesting, and then just some general advice from Marshall about how to participate in and how to design mission concepts and how to participate in other mission concepts out there, and how maybe if you're a new researcher, you want to be able to sort of help out and participate in some of these projects. There's a lot of need out there, so you can be active. All right, enjoy this interview with Marshall Seaton. So if you were to stand on the surface of Enceladus and in your spacesuit and sort of peer down into one of these tiger stripe chasms as it's geysering material off into space, what would you see? What would it look like?
You'd probably get smacked in the face by a bunch of ice coming out. It's traveling really fast.
So you would feel it. Like you could put your hand out and you would feel the blast of the ice particles?
I mean, presumably, yeah, you'd feel something because it's generating this continuous plume and stuff's traveling really, really fast out of there. I mean, the vapor is like 5, 6, 7, 8, 900 kilometers per second coming out of there. And the ice grains are slower because they're heavier, but there's definitely stuff coming out of there. Yeah.
Right. And I mean, is there a place on Earth that would feel somewhat familiar?
Not that I'm aware of. Of course, I don't do a whole lot of exploring in the Arctic or anything like that, but I can't think of any place that.
I've been to like a glacier, and how you get these sort of cracks and fissures forming on the glacier, and you can have these pools of water down below, and it feels like it just goes on forever beneath down there. And I've been to Iceland where you get these geysers that are blasting hot water up so it'd be like mashing those two together.
Yeah, kind of. It's a really interesting place, and we have an idea of how the grains are formed and the vapors expelled up, but we haven't really nailed the compositional link between the two, because you have like this surface of this liquid water reservoir, and then there are these vents that come like where all of the vapor and grains climb up to the surface, and that's part of what people are trying to study right now is like how that like what that vent structure actually looks like, because we don't know exactly.
Yeah, so I guess the answer is you'll get back to me once the mission has completed its science objectives.
Once somebody goes up there and figures out what's going on,
Yeah. So let's talk about the science case for Enceladus. Why is it the most interesting place that we should investigate in the solar system? And that, like, I'm not even putting that to a vote. That's no controversy. That is 100% true. Facts. We have to go back to Enceladus. Why?
I don't necessarily disagree with you, but I will say ahead of time that the views that I express here are my views. They don't represent the priorities of NASA, JPL, Caltech, or any combination thereof. And all the planetary bodies are unique and awesome in their own ways. But Enceladus is super awesome.
But Enceladus is the best. Yeah, I understand.
Okay.
It's just me. I'm saying this. You're not. You don't have to. You can feel free to love all the planets in the solar system, but yeah, Enceladus is just magical. So what's going on? What is making it so special?
Well, I'll sort of give you a chronicling of how we figured all this awesome stuff out. And so I'm going to backtrack to the Cassini-Huygens mission, which was launched back in the 90s. And the goal of that mission was had three primary goals: to study Saturn, to see what was going on at Titan, which I think you've covered a bit about in the past, and to study the Saturnian satellites, which is basically the moons around Saturn. And we didn't know about all this stuff that was going on at Enceladus when the Cassini mission was formulated. But Cassini flew by Enceladus, and there were the thermal anomalies at the South Pole, where there were these regions that were way hotter than they should have been. And when I say hot, I don't mean like hot as we know it. I mean, like, instead of negative 200 Celsius, it was like negative 150 Celsius or something. And so everybody was like, okay, hold up, we got to figure out what's going on. And then then they did another targeted flyby and did some imaging and chemical analyses and things like that. And long story short, they discovered this continuous plume of water and ice that was formed over the South Polar terrain. And we've never seen anything like this really in our solar system. And so it was insane and insanely cool. And then so some follow-up investigations essentially determined that this plume, like, long story short, is sourced from a global subsurface liquid water ocean. And we see oceans elsewhere in our solar system, like Europa very likely has a global subsurface ocean as well. But the difference there is you have to drill through like 10 miles of ice to get the material at Europa. And there's just as compelling of a science case at Europa too. I mean, that's where we literally have a flagship mission that's planned to go there. But the difference between Enceladus and Europa is Enceladus is literally venting samples for us to come pick up and sample. So we have the unique opportunity to directly sample the contents of a subsurface global ocean of an icy moon. And it gets even more compelling than that, because in addition to this global ocean, like, yeah, I mean, in terms of habitability and life detection and things like that, follow the water is the general, the approach that the scientists take. But you don't just need water. You need the chemical elements, like, for life as we know it, at least based on our understanding of life. But you need a source of heat too. And there were some analyses that the Cassini spacecraft and some of the instruments on the spacecraft, the Cosmic Dust Analyzer, did of Saturn's E ring. And it's one of Saturn's rings. And this ring is formed from the plume material that's emanating from the Enceladus ocean. So by analyzing this ring, the material in this ring, the dust and grains, we can see what's coming out of Enceladus, basically. And something really interesting was found in those E-ring grains: silicon nanoparticles with a very specific size range, about 2 to 8 nanometers. And this is important because there's only one place that we know that those silicon nanoparticles of that size range can be formed. And those are in hydrothermal systems, like the ones that we have on Earth, like those chimney things at the bottom of the ocean that host these diverse ecosystems. And so based on that, we know that there's very likely water-rock interactions that are circulating all of this material from the chondritic, from the the rocky core of Enceladus out into the ocean. You have these chemical gradients present because of that. And hydrothermal systems, I mean, there's a little bit of controversy, and I'm not an origins of life chemist, but these hydrothermal systems have been implicated in the origin of life on our planet, or the emergence of life on our planet. And so it's a really exciting place that offers a unique opportunity to sample what's going on without any of the technological constraints with like getting through the ice or anything like that, using a flyby or orbiter mission architecture. So
and even like here on Earth, like if some horrible solar flare supernova wiped out all life on the surface of Earth, those black smokers at the bottom of the oceans would continue on indefinitely as these spots of habitability. They don't care. Mm-hmm. They have no connection to the outside of the planet. And good news, Enceladus is, the surface of Enceladus is freezing cold, and yet it could be having this. That's one line of evidence that you've got this geologic process that is interacting with the ocean at the bottom of Enceladus. But more stuff has been found in the plumes that is even as exciting as that discovery, right?
Yeah. Another thing that was Frank Postberg published a paper 2018 showing evidence for this. But another cool thing, and I'm glad you brought that up, we found evidence for these large macromolecular organic compounds in the plume. They weren't directly detected because Cassini's instruments were older technology, and they didn't have the range to directly, the instruments didn't have the size range or the mass range to detect these large molecules, but they detected fragments of them. And so we have indirect evidence, but strong evidence that there are these large molecules and we don't know where they're coming from. Like, could this be some like geochemical processing that we don't know about? Or is this like, or could there be like critters at the bottom of the ocean, like making these organic compounds? And like, it's really exciting, and it just like strengthens the case for going back to Enceladus.
But even if it's not critters, I know that you've also found dissolved hydrogen gas in these plumes as well, which is food for bacteria. So when you run through this list, like, it is just check, check, check. You've got
you keep bringing up more reasons. Yeah,
I know you've got an active energy source at the bottom of the ocean. You've got liquid water. You've got hydrogen gas. You've got complex organic molecules. You couldn't order up a better list of an environment here in the solar system as a place to go search for life.
It's not bad.
Yeah, we're doing great. So what spacecraft is currently at Saturn right now that we can use to understand these processes better?
Well, unfortunately, a few years back, Cassini did a nosedive into Saturn. And so there is currently not a spacecraft that is capable of doing flyby studies of Enceladus or sampling the plume or anything like that. There's some that are being formulated. And in the most recent New Frontiers call, which is basically NASA saying, okay, guys, give us all your mission concepts. Let's see what you guys are formulating and where we can go. Or not the New Frontiers call, but the most recent decadal survey prioritized Enceladus in its list of priorities for a flagship mission, which is a mission that essentially has no cost cap. Right under a Uranus probe, the second priority is an Enceladus Orbilander concept, which is like an orbiter and a lander. And then one of its smaller mission classes also solicited a return mission to Enceladus as well. So like NASA's aware and is planning to go back, but it's just there are some issues that, like, in terms of figuring out how to sample, how much to sample, like things like that.
But I mean, budgets are always so tight on these space missions, and these flagship missions are very slow moving, large creatures that move through the pipeline, and as they get developed and as the science objectives are nailed down and the technology is improved and there are various even new technologies have to be developed for it's a very long and slow process, and the distance and time that takes to get out to Enceladus. Like even if you launch your mission tomorrow, you're not going to start getting science results for more than half a decade. And everybody's just too impatient for that. So I want to talk about the mission concept that you're working with. So what's it called?
The Astrobiology Exploration at Enceladus, AX for short. Yeah.
And so, I mean, caveats here, anyone from NASA is listening, we understand this is not an actual mission. This is not a mission concept. This is just people hanging out, chatting about cool ideas, what would be fun in scientific paper form. So what is the idea of the AX mission?
Well, it was, I'll give you a little bit of a backstory. And it's what's called a concept study. And what that does is sort of explores the trade space, what sort of instruments, what sort of science you can do under a given cost cap. And so there's never a shortage of science to do. But it's trying to fit all the science in a cost cap. And so this was a result of the NASA Planetary Science Summer School program. And it's not as much a summer school as it is like a rigorous mission design program where they're basically training the new generation of like mission scientists to propose compelling missions. And so it's a competed program, you apply for it, and then your team develops a mission concept. And so we developed back in 2021, the structure, like the skeleton for the mission. And since then, we've been iterating on it and nailing down our science objectives and things like that. And the paper that you saw was basically the culmination of all that. Go ahead. Were you going to say something?
Oh, I was going to say, so let's kind of go through this. So I guess with the Orbitlander being obviously one of the priorities in NASA's pipeline, I've done this long enough that I kind of know how this works, which is that the thing that is the lower priority has to wait a cycle. And so it could very well be that we're going to wait 10 years for the next decadal survey. The Uranus mission is off and away, or at least far enough along development that now the Orbitlander kicks up to the next notch. So I guess what are the clever ideas that you're kind of bringing together to maybe offer up a mission that could solve some of these science objectives sooner than and at a lower budget than everyone sort of originally anticipating?
Yeah, absolutely. And you make a good point. I mean, you can fly by and sample the stuff in the plume under a New Frontiers budget. And so we with this concept, there are four main science objectives. And the first one is directly searching for biosignatures within the plume, chemical biosignatures. And we include a combination of chemical analysis and geophysical and geomorphological investigations to sort of contextualize any sort of the chemical measurements we make. But the first is searching for chemical evidence of life. Can we see like these compounds that we can maybe trace back to what might be a biogenic origin, or what might be biogenic? And then the second, and I can go into more detail if you like. We
will, but yeah.
Okay, all right, cool.
Yeah.
And then the second,
because I'm about to ask you how, but let's go through the high level list of objectives.
Tell them what you're going to tell them, then tell them.
Yeah, exactly.
And the second objective we have is looking at whether the ocean is long-lived or potentially transient. Like looking at the heat budget of Enceladus. It's emitting all this heat and it's generating X amount of heat. And so we want to see if these two values are in equilibrium, if the ocean's been there long enough for life to take hold, or whether it could be like melting or freezing or whatnot. And that's basically a heat balance equation. The third objective is, like we hit on a little bit before, we don't know exactly what the compositional link between this plume material and the ocean is. And that's critical if we're going to attempt to do any sort of life detection investigations there, because if you sample something in the plume, you want to make sure that that it's representative of the ocean composition, and and the associated challenges with that. And then and so we're looking at the vent structure, and then the fourth objective is basically surveying the global crater population, and seeing what it can tell us about Enceladus's past and what's happened in terms of other areas that might have the other high heat flux regions, or whether the ice shell has undergone reorientation in the past or anything like that. And so those are the four science objectives.
Right. And so let's go back around to the beginning then with the one that I'm sure a lot of people are really excited about is attempting to see if you can find some kind of biosignature in the plume. What kind of instruments would you want to be able to do that?
Apologies if I use a little bit of jargon. You have to catch me.
I have a very technical audience, so
okay, good.
if you over jargon, I'll draw you back. But don't worry. Yeah,
okay,
yeah.
Cool.
Feel free to talk about mass spectrometers.
That's where I was headed. And there are a lot of people that are proposing a lot of different instruments, and people have different opinions on what is a good instrument to bring to Enceladus. This is simply my opinion. But if you're going to do any sort of life detection investigation, I'll preface this by saying that Pierre-Simon Laplace stated that the evidence for a claim must be purported to its strangeness. And what that translates to is what Carl Sagan coined, which is extraordinary claims require extraordinary evidence. And so if you're going to claim that you've detected extraterrestrial life for the first time in human history, civilization level science, then you better be sure that it's unambiguous, okay? And
we've seen how that's worked out in the past. Think about the Viking experiment, the Mars meteorite, UAPs, like it goes on and on. Yeah.
Yeah, exactly. And so you want your evidence to be as unambiguous as possible. And one of the best instruments that we have for that are mass spectrometers, because they provide not only like what sort of chemical functionalities might be there, but they give you structural information. They tell you what the molecule is exactly if you have the appropriate mass resolution and things like that. And so it's if you're going to do any sort of life detection mission, you have to have a mass spectrometer. That's like in my opinion, it's got to be on your list of instruments.
And so, like, if I took a scoop of seawater and gave it to you and said, "What can you learn with a mass spectrometer from this gloop?"
What can I learn?
What would you be able to find out? Yeah, I mean, if I said, if I just handed you a glass of water and it contained, right, like a glass of water from the ocean, it's going to contain dissolved minerals, it's going to contain particles that have come from hydrothermic vents. It's going to contain trace DNA from life. It's going to contain all kinds of things, right?
Yeah.
So how would you? And that's the equivalent, I guess, of you sort of flying through the sea spray, with your tongue.
So, like, what information can you tease out of it?
Yeah, what would you be able to discover? Yeah, I'm trying to understand. Like, I guess. Like, how sensitive is this? As you said, you have to be sure. How can you be sure?
Well, it's actually a really complex problem, especially when using molecular biosignatures. Like they're really powerful, but because they allow you to look for life as you don't know it, just by looking for the different distributions of molecules within a sample. But it's not one of those things where you just inject a sample and it's just like this beautiful readout that says biology or not biology, right? It's really complex because you get really messy mass spectrums, and you have this background that's generated by not life. Okay, so you have like all of these geochemical and geological processes that result in chemical distributions, but you have this distribution that's generated by biology sort of superimposed on it. And so it's sort of figuring out what your abiotic background looks like. This is specifically, you asked me what could you learn. I'm just sort of elaborating on how you would do like a life detection experiment, just as sort of a thought experiment. You have to establish what your abiotic background might be, what you expect to be there in the absence of biology, and then establish a quantitative threshold for what you might think, like say there are this is the big hill of signatures from not life, and then you have these signatures for life that are superimposed on it, how to tease those out of your sample. And it's a little easier on Earth because like you can just see tons of amino acids and proteins and DNA and all this stuff. But in a place that's as cold and energy limited as a place like Enceladus, it may not be that cut and dry. And so,
now would it not be as cut and dry because the quantity of organic molecules in the sample is lower, and so it's a very faint signal that you are attempting to tease out? Because I imagine on Earth, if I gave you that jar of seawater to analyze, it's almost like a cacophony of molecules. Every possible permutation of molecules in there screaming simultaneously. That also sounds tricky to sort out the peaks and the valleys when you're looking at the mass spectrometer data.
Yeah, like on Earth, we see there are some really distinct signatures for life as we know it on Earth. Like, for example, you can look at amino acid distributions. On Earth and Earth-based life, you see abundances of some of the larger, more exotic amino acids that are in just the same quantity as glycine, the simplest amino acid. Whereas if you look in meteorites where life hasn't generated any of these organics, glycine is orders of magnitude higher in abundance to these other ones, because it's just simply like more energetically favorable to make. But life doesn't care as much about what's energetically favorable. Like, life cares about what it finds useful for biology. And so that would be a clear indication on Earth. And not only that, we find these complex like biomolecules that if you just like scoop some seawater out, you would see these molecules like, okay, there is no way this could be generated in the absence of biology. So it would be like pretty simple. And so you talked a little bit about abundances of molecules that we would see. The cell densities that we expect based on some modeling that's been done regarding the available energy at Enceladus, the cell densities are likely very, very low. They might be amplified in what we see in the plume based on some things that are happening at the surface of the water table. I won't go like too much into detail, but
right, but like pond scum at the top of the water table.
Kind of, yeah. You might have heard about that before. Yeah. There's like this bubble bursting thing that's been.
I just have ponds. I have ponds and I see the scum. So.
Okay. Yeah. Sure. Yeah. Well, there's an organic film that's likely at the top of the water, like we have here on Earth, and so it sort of concentrates that stuff. But the cell densities are just based on some modeling that's been done. It's just a lot lower there because it's so much colder and it's so energy limited. I mean, here you have the sun, you have like all this geochemical energy that's being produced, and so it's like you just take a cup of water and then you can find it. But it's if life is at Enceladus, it's going to be a little more difficult.
So with the other parts about analyzing the temperature, that sounds like an infrared camera. Counting the craters, that sounds like a camera. What makes this a relatively inexpensive, quick to fall into that new frontiers program? You're looking at a mission that can come in at, what is it, like $1 billion?
Yeah, I think the cost cap for the New Frontiers 5 call was $900 million. Ours came in.
Yeah, so just under $1 billion, right? Which, when you consider, the big flagships run $5 billion maybe the Mars Sample Return mission is getting closer to 8 billion. So, things get expensive.
If you were to land, it takes about $1.1 billion to land a dry paper bag on Enceladus. Right. So, and that's not adding any instruments and whatnot. So this is for a flyby. We had a mass spectrometer and a high resolution camera and a radio antenna, which is like included for radio communication. So it's like half an instrument. So we basically had like 2.5 instruments that we were able to tease a lot of science out of. And part of developing these mission concepts is like, how much science can you squeeze out of what you're able to put on this spacecraft, with the instruments that you have available to you.
So let's talk about like now sort of 30,000 foot view here. You have been approved. It's made it through the system. So how would the whole mission profile work? So, the construction of the mission has been completed. You got your RTG, everything is assembled and together, and it's on your rocket. What kind of rocket are you using? Is it a Falcon Heavy? Is it an SLS?
No, I think it's a medium class launch vehicle that wasn't like specified. I think there's this document you can look where they have like all the different launch vehicles and everything. And if you like go up in mass, you have to like get to a heavier, like a class launch vehicle and things like that. I think ours was like medium class. But we didn't like talk about specific rockets or anything like that.
Okay. And how many flybys of Earth you have to do your gravitational assists?
Oh, you mean like the trajectory? Mm-hmm. Okay, yeah. So with this mission, we would launch in 2034, and then using a Venus Earth gravity assist. So you would have to first go around Venus and then use Earth's gravity a few times to wind up, and then slingshot out into the Jupiter system. And then once you're out into Jupiter, you use Jupiter's gravity to slingshot out into the Saturn system. But getting out there isn't the problem. It's slowing down that's the problem. Because you have to slow down enough to where you can do an orbital insertion to where you can actually like get in a stable orbit. And then after orbital insertion, I think we had a 2-year pump down phase planned, because to target Enceladus with the correct inclination, geometry, altitude, things like that for our flybys, we'd need to use Titan's gravity to slow down for about 2 years, doing multiple orbits of Saturn. And then once all that's finished, then we could enter science operations, where we do a flyby about every 2 weeks.
So you wouldn't be in a tight orbit around Enceladus. It would be a much wider orbit, kind of similar to, say, Juno.
Yeah. It's so the way this mission architecture specifically would work is you're orbiting Saturn, but you're just doing these flybys of one of Saturn's moons in orbit around Saturn. Getting into orbit around Enceladus is very tricky. It's under the New Frontiers cost cap. It is. Because again, you have to slow down to where you can be slow enough to where you can get into a stable orbit around Enceladus, which doesn't really have very much gravity, and so you can do it, but it's a lot more difficult in the context of the budgetary constraints that are imposed on some of these missions.
Yeah, I mean, I think that's one of the geniuses of the Europa Clipper mission is stay in orbit around Jupiter, but make those flybys of Europa on enough of a regular basis to build up that science. And I think we're seeing this same idea showing up more and more. And it makes a ton of sense, exactly. As you said, if you're to actually slow down, you need a bigger rocket. And if you need a bigger rocket, then it's going to get more expensive.
It takes a lot of fuel too.
Yeah. That's the hard part of getting to any of those destinations that you want to get to, is that a flyby is a fraction of the price of going into orbit, and yet in orbit is orders of magnitude more science, and you've got to always make that decision either way. So you've arrived at the Saturnian system. You've done some orbital mechanics using various moons to tweak your orbit. You're now in this really wide orbit around Enceladus, flying through the Saturn system. So how would the science operations work with the mission?
for ours, we have like a minimum number of flybys that we need to accomplish our science. So typically, you get more science out of it than just the minimum that you propose. But we have in our concept a minimum of 5 plume fly-throughs where we would collect, I think, 240 mass spectra per plume or per flyby. And then in addition to that, we have, like I talked about, vent morphology. We would also have some high resolution imaging science of the south polar terrain planned, because throughout Enceladus's orbital phase, we expect these vents that you talked about at the South Pole, that all that ice is shooting out of into space. We expect those throughout Enceladus's orbital phase, due to tidal forcing, these vents should be opening and closing like this. And so we want to see if we could, and there are different mechanisms of their formation that we expect to be occurring. And so by looking at the morphology and how they're opening and closing and things like that, we can sort of tease out what the underlying plumbing mechanism would be. And so we have some, in the concept, some high resolution imaging flybys at low altitudes planned for that as well. And then also a minimum of 22 flybys. Well, it doesn't have to be exactly 22 flybys, but 22 flybys would be required for the imaging to do to survey the global crater population, to do the crater science that I talked about. And then we required a minimum of 30 flybys for our gravity science to see, to look at the ice shell thickness of Enceladus and
Wow.
see what the heat balance might look like.
So like 4 to 6 years or so to kind of really build up the whole science case. Is that right?
I think we had 4 years of science operations planned.
Yeah. Yeah.
Yes.
But I mean, it'll have I'm assuming it's going to have an RTG because it's so far away from the sun. You can't power this on solar panels. So, I mean, the Voyagers are still going. So who knows how long it'll last.
Yeah, I think there's a concept I read that uses solar panels. They just have to be like really big. I don't remember which.
So, for example, like at Jupiter, it's 25 times. So the solar panel surface area for a mission that goes to Jupiter has to be 25 times as big to provide the same amount of power as what it would be at Earth. Yeah. And so I should do the math at some point, but I'm sure it's in the 100, low, high.
We did the math in the paper. I forgot what the value actually was, but it's like not super efficient. But I know that there are concepts that utilize it in combination with an RTG or something like that. But yeah, we use an MMRTG.
It's interesting though, because you do have like a couple of weeks to recharge the battery. When you think of like Ingenuity, for example, that is powered by a little battery and a little solar panel, and it just sits on the surface of Mars until it has enough power, and then it's able to take off. I wonder if you could have your spacecraft just store power over the course of 2 weeks and then into its battery system, and then it's going to do its flyby, and then it has to sort of deliver all that power to do the science, and then it, digests what it found for the next 2 weeks and then comes back around. So who knows? Because it doesn't have to be active the entire time. So it'd be interesting to see where that.
You have like minimum like operating levels that whenever an instrument isn't necessarily like operating, but it needs to be like kept to a certain temperature in the spacecraft, like the subsystems all need to be kept up to a certain temperature and things like that. So there's like a non-zero amount of energy required while it's like not during flyby operations. But yeah, you're right.
Yeah. And there are some interesting, even through NASA, they're doing a lot of really interesting work in other types of RTGs. So not just the traditional plutonium-238, like there's different some people are proposing different flavors of RTGs using different isotopes that will deliver a different heat profile and have a half-life that lasts a different amount of time. And so, it may very well be that in the future you'll be able to kind of go like, I want something that's going to give me a lot of power but only last 12 years, as opposed to less power but it's going to last 50 years or however long the voyages are going to last.
Oh, that would be sick, because I mean, a lot of the people sometimes think that whenever you are going out to do some science in space, you just like take some instrument you have in your lab and you just slap it and like duct tape it to the spacecraft and it just goes out and does its thing. But it's a lot more complicated than that, because like you said, you have a finite amount of power that you have in your spacecraft that has to go to empower all these subsystems. And so power constraints are a serious deal. Mm-hmm. And so
they're the top three priorities for missions, right? Like the number one priority for mission is power, and the second priority is power, and the third priority is power. Right?
Yeah, it's tough. It's tough. And then after that you have size and like volume and all that, and mass, and of course, but yeah. It's that would be very sick.
But
of course, I don't need one.
Yeah, but I mean, and I think like from my perspective, when you go back to that idea of the orbital lander, it kind of takes you back to that controversy that happened with the Europa Clipper and the idea that they would attach a lander to the Clipper before they really knew where they wanted to land. It feels like a wise move to send out a mission that's almost in the spirit of the Europa Clipper, but more specialized for flying through plumes with its tongue out, to then chart the terrain for that a lander, a perfectly chosen lander with maybe a little more weight than a paper bag, can set down and continue the mission.
Yeah, I think that's sort of what the orbital lander concept is they want to, I mean, based on my understanding, is they want to have the first phase of the mission be like an orbiter type architecture where they do survey all of the surface at high resolution, everything, and identify these optimal landing sites and things like that. And then once they've done their orbital science and surveyed and done all this high resolution imaging and identified within that 2-year time frame or whatever it was, I can't remember exactly, then within that time frame they're able to select their landing site, and then they land and do all their landed science. And
right.
So
and communicate with the orbiter, and you've got this nice relay back to Earth.
Yeah.
So
exactly.
So you say launching in 2034. So when does that? Yeah. When would you arrive at Enceladus?
A 12-year cruise phase, so 2046. And a lot of the mission, at least based on the launch windows we have in the next couple of decades, if a mission is selected this year to Enceladus, we're not getting data back until 2050.
Yeah.
And so it's tough.
Now, you talked a bit about sample return. Is that can't be in your proposal?
No. That's like a whole nother, God, I can't even imagine what that would look like.
Right. Yeah.
It'd be sick. But
no, absolutely. Yeah. Well, I mean, it's the same thing. Like, you look at the Mars sample return mission and you just think, like, it is such a complicated thing to have Perseverance roaming across the surface, picking up samples, taking them to a ground site, handing it off to a rocket, the rocket flying off. There's a lot of moving parts. And yet, can you imagine having whatever it is, 30 samples of the most interesting places that geologists could find in the place that's most likely to have evidence of past life on Mars in the hands of scientists in the best laboratories on Earth? Yes, please.
Yeah, exactly. And that's why the Mars community is so I'm not even in the Mars community really, and I'm stoked for it. I mean, it's because there's so many limitations that are imposed on spacecraft instrumentation. Like I said, it's more complex than just like putting an instrument, just putting on a spacecraft and sending it out. These huge instruments that we have on Earth in our laboratories, they're like, you have to make them like this big to put on a spacecraft, And so you don't have near the sensitivity. you don't have the same mass resolution, for example, for a mass spectrometer. Like down here, you can like tell exactly what a molecule is, like just by putting it in there. And up there, like we don't have the, just because of how robust you need to make these instruments, you're not afforded the same luxury of how insanely sensitive these instruments on Earth are. And because the stuff you put on a spacecraft has to withstand thermal cycling, going from super cold to super hot environments. It has to withstand these extreme G forces when you're like vibrations, when you're in orbital insertion and things like that. And so being able to take samples from an extraterrestrial environment and take them back to Earth where we have these incredible instruments, like it's like a dream. It's like career. I think there's a term that I've heard used, career catharsis for a lot of people.
Right. I mean, I think about like, say the Hayabusa 1 mission, which was just barely able to pick up less than a gram of material from asteroid Itokawa, bring that back. And yet astronomers were able to then work with that, with just these crumbles at the bottom of the collection plate, to make these incredible discoveries about the formation of the solar system. And now with the samples from Hayabusa 2 with Ryugu, where they actually got a nice little cup's worth of material, they've found so many amino acids, they've found interstellar grains, they've found just all of these really interesting things that have helped clarify where the water on Earth came from, what the earliest phases of the solar system look like, that you just couldn't do with any of these flyby missions.
It's like a time capsule. I mean, if you have the instruments that like these Earth-based instruments that you can actually use to figure out exactly what's there, then it's so much more of a science return than just like using these instruments that are extremely advanced technologically but don't have the same capabilities as the ones we have here.
Do you think that these kinds of hydrothermal vents are more common across the solar system than we know? I mean, we know that we have hints of them at Europa, and when the Voyager 2 spacecraft went past Neptune, it saw some kind of geyser activity on Triton. Do you think that this is the rule, not the exception, with these ocean worlds?
I can't make a claim that hydrothermal activity is more widespread than we think, because especially in the outer solar system, like I said, it depends on like the tidal energy, like the orbital eccentricity and things like that, and depends on what the structure of the moon is. But I think that based on what we know now about ocean worlds, that ocean worlds are a lot more common than we thought before. And so whether there's hydrothermal activity on those ocean worlds or below the surface, I don't really know. But based on what we're learning, it's sort of transforming our understanding of planetary habitability, because for so long it was just like this Goldilocks zone where you had standing liquid water on the surface, like a certain distance from a star. But now we're finding all of these outer solar system planets that have like these moons that probably, like a lot of them, I mean, we're going to learn so much whenever we go to Uranus about, like, I'm sure we're going to find a ton of ocean worlds there too, but they're a lot more widespread than we think. And so there are probably, like, based on our current understanding of habitability, a lot more habitable ocean worlds than there are Earth-like planets. And so they're a compelling destination to look.
Yeah, all of the conditions are there for life. They're quite robust because they have that protection of the ice shell, and as long as there's some kind of energy input coming from their orbital interactions, which are everywhere, then it makes sense that these things are going to be all over the place. They're just brutal to try to investigate. And back to why Enceladus is such a gift. right?
Exactly.
Like
That's why Enceladus is so cool. It's like we don't have to drill through 25 miles of ice,
right. Um,
Which I'm sure
I mean,
that, the NASA engineers are brilliant.
Oh,
But
I've done some wonderful interviews with people who have some great ideas, and you would listen to one of those interviews and you'd be like, "Yes, let's do that. That sounds great. All of the pieces are there. We're ready. I've got my nuclear fusion power tipped descending bot that can go through 10 kilometers of ice, no problem. I'm ready." But it's and yeah, that would unlock everything. But then you sort of extrapolate this idea out to the wider universe that probably every star system out there has dozens, if not hundreds, of these ocean worlds, all locked under ice, all inaccessible from our perspective. And the one that we have is this gift. For now, for sure. Yeah, wait till the warp drives show up.
But yes, but based on our current technologies, like Enceladus is definitely a gift, and it's a unique opportunity to study the subsurface ocean of an ocean world. It's the only opportunity we have right now, because Europa has some transient plumes that have been identified, but based on some research that was done in the past couple of years, those plumes aren't likely connected to the subsurface ocean. They're more likely connected to these brine pockets within the ice shell. And so yeah, I'm based on what we know now. It's the only opportunity we have. Is
now, is there something special about Enceladus's orbital environment? That, I mean, I know one of the big questions that you have is like, can we investigate how long these plumes have been around? Is this a thing that's been around for hundreds of millions, billions of years, or is this something that just showed up a million years ago because the heat built up to the point, like a hotspot, like the Hawaiian Islands, right? Do we have a sense that there's something special about the orbital dynamics of Enceladus that pushes it into this kind of activity?
Well, that's a bit above my pay grade. I'm a chemist, but I can do my best. Well, we know that the plume is at least at Enceladus has been active since the Voyager, because it's really funny actually, because when the Voyager spacecraft passed by Enceladus, like people were looking at after the plume was discovered more recently, looking back through old Voyager photos, and we actually saw the plume with Voyager, and nobody caught it. It's just this one pixel on Enceladus, and so we caught it. So we at least know it's been active since the Voyager or one of the Voyager spacecraft passed by it, and we know that it is still active based on the James Webb paper. I think it was just released like last month, where it imaged the plume. But outside of that, I'm honestly not really sure.
Yeah,
about
but I guess I just wonder if like each one of these ocean worlds, whatever are either the radioactive decay that's happening inside the world, or the tidal flexing that's happening with its interactions of the planet that it orbits, that the heat builds up until it inevitably has to vent. And then it goes through some kind of venting period for some period of time, and then it's removed all of the excess heat, and then it seals off again, and then it waits until the next time and so each one of these worlds in turn will go through this process. Like if they still have any kind of radioactive decay or tidal heating that's happening inside of them, they will all take their turn to vent. And maybe we see the evidence in the rings of the giant planets. I don't know.
Yeah, no, that's a cool question, because it's like if you heat a closed system, what happens?
Mm-hmm.
So my first
at some point release. Yeah.
Yeah, I mean, if more heat's being generated than is being dissipated, this is assuming an icy body, then you would first have melting of the ice shell before there would be any sort of like expelling material. I would, based on my understanding. I'm not a geophysicist or anything. I have some brilliant geophysicist friends, But I think we talk about this in the paper a little bit. Is if you have this disequilibrium in the heat budget, you would just have melting of the ice shell. But in terms of like expelling material from the subsurface, I'm not really sure. Yeah. Now I'm curious. I'm gonna have to go ask somebody about this.
Great. There you go. I've done my job then. So, we were very careful to say that this is a concept that, as part of a really fun program, a bunch of people looked at the constraints and tried to figure out what would be possible. What could be the next step if perhaps you can convince other people that not only is this possible, but actually of the range of options to explore Enceladus or other planetary bodies, this one makes sense? What would be like a next step that you would be hoping to see? Like, you just put your paper out there and you're like, that's it, I'm moving on to figure out whether other planets will have hotspots, or, what's the next step, do you think?
Well, for me, specifically, I'm actually, there are some other Enceladus mission concepts that are currently being developed and are pretty far along. And I'm actually, in my research, I'm supporting one of those at the moment, and working with the team, trying to nail down some science with respect to those.
And this is a pretty common thing, though, right? Like you put a bunch of ideas in paper form, which is a very kind of elegant way to express some suggestions. And then the people who are working on those missions look through and go like, hey, could we incorporate some of these ideas into what we're working on? Do you want to come on as
that's what I wanted,
member of the paper? Yeah.
Yeah. So
that's what you're experiencing.
That's what I wanted to do. And because I'm really proud of the work that we did, nailing down all these measurement requirements and things like that. And I think I right now, I don't think I want to necessarily work on proposing this. But
principal investigator.
No,
Alan Stern,
Yeah. See you, Chris. No Christmases, no holidays. 20-hour work days now.
Push through the machine.
Maybe one day.
All right.
Maybe one day. I don't know. But one thing that I really wanted to do with this paper is that normally, when people are developing their mission concepts, it's really hush hush. And they have their own methods of establishing measurement requirements and everything like that. And so there isn't a lot of that in the literature showing how you take science questions and deriving measurement requirements for how you would answer those science questions. There's not a lot of that out there. And so I'm really proud of the work my team and I did, nailing down those measurement requirements and showing not only future PSSS cohorts, Planetary Science Summer School cohorts, but also the greater scientific community, how you take science questions and how you can actually translate that into measurements that you can make with a mission and how you can answer those science questions, if that makes sense.
I mean, I think that, my perspective again is people are working on different aspects of the mission, and various parts are boxes that are just we'll figure this out later. And for you to show up and go, whatever mission it is, if you want to get a robust detection of life, it's going to need this many samples, this amount of time, this quality of mass spectrometer data.
Yes.
Plug this in, and hopefully that will solve the question mark portion of your paper that you were planning to work on later. And I'm sure it's much appreciated to hand that over to people.
Thank you.
And it's interesting to me. I think about people who are earlier on in their career who want to be a part of these kinds of missions that are quite exciting, or want to be a part of this kind of science. Do you think that it's easy to find these gaps where somebody needs to do the legwork to deliver this kind of information? Is that a good direction? If you're sort of newer in the field, if you're, freshly graduated and you're trying to participate in the scientific process in the community. Is this a good approach to go?
I would say that, so if you'd have told me 5 years ago that I would be working on this stuff, you'd have to sedate me.
Because you'd be so enraged, or because you would be
because I've been so stoked.
Okay,
no,
right.
This stuff's great. But I think that, are you speaking to like people in graduate school or people that have finished graduate school? Or what
I mean, I think that like the impression that I get in talking to a lot of scientists is that there is this publish or perish requirement, and sometimes you don't know what to write about. You don't know where to direct your energy because you're not sure what's going to make a difference. But one way is to solve someone else's problem, to kind of find people that are working in the same kind of area that you are, see where they've got this just, TBD to be done later, and fill that gap for them, right? To answer those questions for them, to deliver what it is that makes their lives easier and helps push their mission forward.
Yeah. I mean, that's how I ended up where I am now, is doing just that. I mean, if you're interested in doing mission science, first of all, I would strongly recommend the Planetary Science Summer School program. It is competed. You do have to apply for it. And it's a pretty small cohort, but that is a really awesome way to get your foot wet in terms of like mission science specifically. But what you mentioned about in terms of like just career advice, yeah, I mean, that science is identifying gaps in human understanding and then trying to fill those gaps.
Yeah.
And that's what we try to do with this mission concept. I mean, that's what we started, is like, what do we not know about Enceladus, and then everything else kind of followed, so.
Yeah. And I guess that's what, I mean, that's the kind of thing that I'm really interested in, practical advice, practical ways that people can take action in this field that they've chosen to make a difference. And whenever I hear something that feels very actionable, very tractable, I sort of latch onto it, because now I'm sort of thinking about this as like, people ask me, like, I want to be an astronomer, I want to be an astrophysicist, I want to be an engineer, or I'm an engineer and I want to get involved. I'm a computer programmer. How can I get involved in missions and find places where people have put question mark in their work, TBD, and they need help, and you can deliver them results.
The best advice I could give is meet those people and go up and talk to them, because that's how I ended up where I'm at. When I first started grad school, there was this guy that was the PI of the Icy Worlds Astrobiology Center thing. Then he gave a talk at Georgia Tech, where I was in grad school. And I just went up and said, "Hi, I'm Marshall," And I asked him a couple of questions, and he's like, "Cool, you want to come work at JPL over the summer?" Like, and then I went out, and my girlfriend had to sedate me and everything,
Yeah, right.
But a lot of it's just like, if you talk with people and if you are genuinely enthusiastic, and you care and you're interested in that, then it's infectious. And so, that's the best advice I could give, is you'd be surprised.
I 100% agree with you. It feels like that's my career so far, and it's working out all right for me. I haven't gotten the invite to go and actually spend a summer designing spacecraft, but now I think I want to apply. That's fun. So see if they need a space journalist. Well, Marshall, it's been a pleasure talking to you. Yeah, thank you. And good luck with either this exact mission flying by 2034, or at least bits and pieces of it joining the collective and being part of this mission. I cannot wait until we get more information about Enceladus. So if you discover life on Enceladus, will you let us know?
Yes. I'll be sure to keep you posted. Thank you so much for taking the time to have me. I've loved nerd out about this stuff. It was a pleasure.
Right. Wonderful. A huge thanks to everyone who supports us on Patreon and helps us stay independent and keeps ads at a bare minimum. Thanks to all the interplanetary researchers, the interstellar adventurers, and the galaxy wanderers. And a special thanks to Joel Yancey, Antonio Lofilara, Dustin Cable, Just Paul Davis, Vlad Shiplin, Jay Dennis, David Giltonan, Modso, George, Jeremy Mattern, Jordan Young, Tim Whalen, Dave Verabioff, Andrew M. Gross, and Josh Schultz, who support us at the Master of the Universe level. All your support means the universe to us.